So, good morning, or whatever other time of the day you're watching this, everyone. Uh, Welcome back after your extended spring break. As I mentioned in my email, this is not my favorite way of trying to teach a class, but we'll have to make the best of it and start up where we left off last time. So, 2 weeks ago, we started talking about acids and bases, and we're going to continue that now. In particular, we're going to focus on weak acids and bases, which we began talking about at the end of last time, but I'm going to go back over some of this again just to remind us where we're at here. So, all that we're going to be focusing on will be Bronsted acids, which means proton donors, and Bronsted bases, which are proton acceptors, as we talked about before. So, for an acid, as we know, an acid will dissociate in water, HA is the acid, water, to form hydronium ions and the conjugate base of the acid HA. So HA is acting as the Bronsted acid, water as the Bronsted base. It's accepting a proton to form hydronium ion, and the HA, in donating a proton, forms its conjugate base, which is A minus. So the equilibrium constant for that, as we talked about before, the case of A, technically involves activities, but we're going to assume that concentrations are all we have to worry about all the time. So the Ka then is essentially equal to the hydronium ion concentration times the A minus divided by the HA. The water, of course, as a pure liquid, does not enter into the equilibrium constant, even though it's part of the reaction. So, as we talked about again last time, the pKa of the Ka is minus the log of the Ka. The lowercase p in front of any term, like Ka, always refers to minus the common log of that term. So the pKa means minus the log of Ka, just like pH means minus the log of the hydronium ion concentration. So the difference now between strong and weak acids is simply this, as we've discussed before. In the case of a strong acid, when it reacts in water to form hydronium ions, there are essentially no HA molecules left. And so the HA concentration that remains is much less than the hydronium ion concentration that they produce. This is for something with a Ka much greater than 1, which is a strong acid. Weak acids, as we said, are just the opposite. They dissociate only very slightly, depending on how strong or weak they are, so that at equilibrium, which is reached almost instantaneously, by the way, in solution, for a weak acid, the remaining concentration of HA at equilibrium is much greater than the hydronium ion concentration that it produces. So Ka in that case is much less than 1. Now, bases are just the other way around, of course. Here's a weak base, or any base for that matter, B. Here's water, which acts now as an acid, so that the base B accepts a proton from water to form the conjugate acid of B, which is Hb plus, and leave behind the conjugate base of water, which is hydroxide. So similar to the situation for the weak acids, the case of B, which is the equilibrium constant for the weak base, again, strictly speaking, should involve activities, but we're going to assume that it's essentially the same as concentrations. So the Kb involves concentration of the Hb plus, the conjugate acid of the weak base, times the hydroxide concentration here, divided by the concentration of the base itself. And again, water does not enter into the equilibrium constant. So in this case, there's a Kb, and so the pKb is minus the log of Kb. So it's exactly analogous to the situation with the acid. So in this case, a strong base is one in which the acceptance of a proton is almost complete, or virtually is complete, from water to form Hb, so that at equilibrium, the concentration that remains of B is much less than the Hb plus concentration. And so the Kb is much larger than 1 for a strong base. For a weak base, just as for a strong acid, or for a weak acid, excuse me, the concentration of B at equilibrium is much greater than the Hb that would result when it reacts with water. And so the Kb is much less than 1. We've talked about this before. So that, in essence, a little cartoon here that we looked at once before shows that for a strong acid, the HA concentration before dissociation, and then after dissociation at equilibrium, there's essentially no HA left, and there's only H3O plus and A minus. But for a weak acid, the concentration of HA changes only very slightly when it reaches equilibrium. The concentration of H plus and A minus are very small. So it's just the comparative relationship between strong and weak acids. Now, this is a table taken from another book that shows a whole series of weak acids. Here's the HA, here's the formula for it. Here's the name of it over here. And here's the conjugate base for that weak acid. You'll notice that the acids that have very large Kas, much larger than 1, are very few. In fact, there are only a handful, less than a dozen, of strong acids that dissociate completely in solution. And that's why they're shown, in fact, the concentrations of HA that remain at equilibrium are so low that they're very, very difficult to measure. And that's why all the Kas are shown with an approximate sign in front of them. Hydroiodic, hydrobromic, perchloric, and so on are 10 to the 7th or 9th or 11th, very large. So the pKas are actually negative numbers because it's minus the log of the Ka. And so you can see here that there's only about 6 or 7 or 8 that are shown here. By contrast, the weak acids, and this is just a small selection of them, by the way, the weak acids are much more numerous. There's all kinds of hundreds, thousands of weak acids, most of which are organic compounds of various kinds. You'll learn more about that when you take organic next year. But all of these are ones that have Kas that are less than 1. In fact, some are much less than 1, as we'll see in a minute. Iodic acid, HiO3, is the Ka is 0.16. It hardly qualifies as a weak acid, but it's definitely not as strong as a truly strong acid like up here. But as you go down the list, these are arranged in the order of decreasing acid strength. So, for example, acetic acid, which is right here, one of the most common weak acids. The acetic acid HA is CH3COOH, and the conjugate base is the acetate ion, which is this. And the Ka is about 1.8 times 10 to the minus 5. That's a number you'll eventually remember because it comes up so often. And so the pKa for acetic acid is 4.75. But as you go farther down the list, you can see there's some others here that are much weaker yet. Hydrosulfuric acid, H2S, which is actually a gas, of course. If it dissolves in water, it will form some hydrogen sulfide ion, but the Ka is on the order of 10 to the minus 8 or something. And so it's a much weaker acid, about 1,000 times weaker than acetic acid, for example. Finally, at the bottom of the list is shown water. Technically, as we've seen, water can act as an acid or a base. When it acts as an acid, here's the HA, here's the conjugate base, and of course, its Ka is 10 to the minus 14. That comes about because of the fact that the OH minus and H3O plus concentrations, the product of those two, is 10 to the minus 14. So here are some, very few weak bases. It's not true that all weak bases contain nitrogen, but many or most of them do. The ones that are shown here are all monobasic nitrogen bases in aqueous solution. Again, one of the commonest ones is ammonia, which dissolves in water to form ammonium ion and hydroxide ion. The Kb, and again, this is a number you'll wind up remembering a lot because it happens to come up often, and it just so happens, purely coincidentally, that it has the same K value as acetic acid does, except that it's a Kb instead of a Ka. The rest of these are all various organic compounds that are all amines. An amine is simply an organic compound that contains nitrogen with one or more hydrogens attached to it. So this is methylamine, this is ethylamine, and so on. And then there are some others. You'll notice that as the number of methyl groups attached to the nitrogen increases, the Kb actually decreases somewhat. So that for trimethylamine, which has 3 methyl groups, instead of ammonia, which has none, only has 3 hydrogens, it's something on the order of almost 100 times weaker of a base than ammonia is. Glycine is an example of an amino acid. I'm sure you've all heard of amino acids. It happens to be the simplest amino acid. It's basically a a weak acid that contains this OOH group again, and it contains an NH2 group attached to this CH2. So if the NH2 weren't there, and this was CH3 at the end, you'd have acetic acid. So glycine is essentially just amino acetic acid. And you notice that its Kb is much, much lower than most of these others. So something must be making it behave as a much weaker base than ammonia. We'll get to that, talking about the reasons for that later. So now we're going to go back to talking about something we brought up now several times, and that's this whole concept of conjugate acids and bases. As we said, the conjugate acid of a weak base is the acid that forms when the weak base donates a proton, accepts a proton. A conjugate base is what's left when a conjugate acid loses a proton. So, for example, here's the dissociation for some acid, some weak acid, or strong acid, it could be as well, HA. It reacts with a base. In this case, water is acting as a base. As we know, water can act as either an acid or a base. And so the water is acting as a proton donor. The HA is, the water is acting as a proton acceptor. It accepts a proton from the HA to form hydronium ion, which is the conjugate acid of water. The conjugate acid is simply something that has accepted a proton when it was acting as a base, accepts a proton to form, in this case, H3O+, and A-, which is the conjugate base of HA. So the conjugate base of anything is what remains when it has donated a proton. Now, it's important to keep in mind that because of the equilibrium in water and because of the self-ionization of water itself, as we'll talk more about later, any conjugate base or conjugate acid of something else has its own Ka or Kb. So that the Ka for this acid HA, as we've seen before, is the hydronium ion concentration times the A- over the HA. But at the same time, this conjugate base that was formed from HA can behave as a base. It's in solution. It acts like a base by accepting a proton. In this case, the water is acting as an acid by donating a proton. And so what forms is the conjugate acid of A-, which is HA itself. And what forms after the water has itself donated a proton is its conjugate base, which is hydroxide. And so it's important to keep in mind, and we'll see the reason why this plays a large role later on. It's important to keep in mind that when an acid in aqueous solution acts as an acid by donating a proton, the water accepts one, you form the conjugate acid and the conjugate base. However, the conjugate base of HA can act as a base. It can accept a proton. And we'll see that it doesn't necessarily have to be that it accepts a proton from the same thing that donated it in the first place. We'll talk more about that later on. So when A- acts as a base, it's accepting a proton from the acid water to form its conjugate acid, HA, and leaving behind the conjugate base of water, which is OH-. So the Kb for that conjugate base, just as the weak acid itself has a Ka, its conjugate base has a Kb. So the Kb then is the concentration of HA times the hydroxide over the A-. Now, what's important is that, for reasons that we'll see in a minute, the stronger an acid is, the stronger HA is, the weaker is its conjugate base. That means that for a strong acid, its conjugate base is a very weak proton acceptor. Similarly, the weaker an acid is, the stronger is its conjugate base. In other words, it's a strong proton acceptor. And because of the self-ionization of water in solution itself, you can never have an aqueous solution that does not contain hydronium ion and hydroxide ion in concentrations that have to, the product of which has to be 10 to the minus 14, as we've seen before. So the Ka here times the Kb of the conjugate base, we can multiply those two together. That's just this expression times that one. And you'll notice that what happens, of course, is the A- concentrations cancel, the HAs cancel, and all we're left with is hydronium ion times OH-, which is Kw, as we've seen before. And we know what the value of Kw is. It's 10 to the minus 14, which means that if I add together the pKa of the weak acid and the pKb of the weak base, because these are now logarithms instead of concentrations themselves, adding them together is the same thing as multiplying them. And so just as Ka times Kb must equal Kw, pKa plus pKb equals pKw, which has to be 14. And so that's what leads to this conclusion right here, that the larger one of these is, the smaller the other one has to be. So if an acid is sufficiently strong, its conjugate base will be weak. And if it's sufficiently weak, its conjugate base will be sufficiently strong. So this is going to play an important role in aqueous solutions, as we'll see, because it can never be escaped in aqueous solutions that the product of the hydroxide and hydronium ion concentrations is always 10 to the minus 14. Anything that makes one of them higher must make the other one lower. We'll see that that's important as we go along here. Here's just a simple little example of 5 different materials to illustrate that. First one is chlorous acid. Chlorous acid is HClO2. So when it acts as an acid, it donates a proton and forms the chlorite ion, ClO2 minus 1. And if you look at the pKa for chlorous acid, it's about 2.00, which means that the pKb of the chlorite ion must be 12, because the sum of these two has to always be 14. Okay? Here's another example. Here's our friend acetic acid again. Acetic acid, of course, has a pKa, as we've seen, of 4.75, which means that the pKb of its conjugate base, which is the acetate ion, has to be 9.25, so that the sum of these two is 14. Here's hypochlorous acid, which is HClO. That's the stuff that's in common bleach. Hypochlorous acid is a very weak acid. It has a pKa of 7.5 something. And so the pKb of its conjugate base, which is the hypochlorite ion, is 6.47. The sum again is 14. Now we get to something that really acts as a base most of the time, ammonia, which we've talked about before. The ammonia itself, and we'll start on the blue end this time, ammonia itself has a pKb, as we've seen, of 4.75. So that it means that the pKa of its conjugate acid, which is ammonium ion here, has to be 9.25, so that the sum is 14. And again, here's methylamine now, which as a base, it can form its conjugate acid of methylammonium ion, and the pKa of that is 10.56, which means the pKb of methylamine must be 3.44. So the interrelationship between these is important to keep in mind, because it can never be escaped. All of the relationships between these ions in solution is always governed by this fact that the concentration of hydronium times the concentration of hydroxide always has to be 10 to the minus 14. Here's another little figure that shows the approximate relationships between these. Here it shows HCl at the top, which is, as we know, is a very strong acid, so that the acid strength is high. It means that its conjugate base, which is the chloride ion, is a very weak base, so weak, in fact, that, as it said here, it's ineffective as a base. What that means is that in solution, the chloride ion essentially never accepts a proton to form any HCl. All right. As you go down the column here, the acids are getting weaker and weaker. This is hydronium ion itself, which has a pKa of 0. The reason is that when the hydronium ion concentration is 1 molar, it must mean that the hydroxide is 10 to the minus 14 molar. So the log of 1 is 0. That's why the pKa of hydronium ion itself is 0. And so the conjugate base of hydronium ion, of course, is water. Water is a very weak base, as we've seen before, and we'll see some more later. But as you go down the column, the acids are getting weaker and weaker and weaker. This is hydrogen sulfate, which is the conjugate base of sulfuric acid, in fact. This is hydrofluoric acid, which is a moderately weak acid. So its conjugate base, which is fluoride, is a very weak base, right? It's not so weak that it's ineffective as a base, but it's still very weak. Going down still farther, the acids are getting weaker and weaker. Here's the ammonium ion we just talked about. Here's hydrogen peroxide. And then here's water itself. Water itself is a very weak acid. And for that reason, its conjugate base, hydroxide, is a very strong base, as we already know. And the reason that its pKa is 14 is that when the concentration of hydroxide ion is 1 molar, the concentration of hydronium ion is 10 to the minus 14. So pKa of water as an acid is 10 to the minus 14. Finally, for things that are very, very weak acids, hydrogen is a little bit difficult to explain at this point, but for things that are that weak, their conjugate bases are very, very strong. A hydride ion, for example, is a very strong base. Okay, I'm not going to go through all of these. This is similar information with lots of different materials represented here, but in this case, I included it in the lecture notes because it shows actual values of the Ka and the pKa, and it shows the same trend that we were just talking about. The acid strength here is increasing as you go up the column, and so the conjugate base strength is increasing as you go down the column, like that. And you'll find many of the same numbers we looked at before are in this table somewhere. Now, one of the things that we're going to spend more time a little bit later talking about is this phenomenon right here. And we'll just briefly describe it so that we can understand a little bit about why some acids are stronger than other ones, even though they're all weak. All things that we've lumped together and call weak acids, they're not all the same. As we've seen, the Kas range from 10 to the minus 14 up to 10 to the minus 2 or 10 to the minus 1 or something like that. This means that the acid strength is varying by many orders of magnitude. What causes that? Well, this is a very simple schematic representation of some molecule, call it XOH, where X is something that can come off possibly as a positive ion. But if this XOH dissociates by the XO bond breaking, like this, it produces this X plus ion, whatever that may be, and a hydroxide ion. In that case, this thing is acting as a base, of course. An example of this might be sodium hydroxide, where X is sodium, for example. And so it means that this XO bond is very weak. In fact, it's so weak that sodium hydroxide in solution actually dissociates into ions like this. It doesn't need any help at all. The water itself doesn't. On the other hand, if the strength of the OH bond is weaker than this bond right here, it now will be that the OH bond breaks to form XO minus and H plus. This material is acting as an acid. It's donating a proton, and here it is, and leaving behind its conjugate base right here. Now, the point of all this that we'll get to in a minute is that anything that makes this bond weaker makes the acid stronger. Anything that makes this bond a little bit stronger makes the acid weaker. And so to look at a simple example that shows the so-called hydrohalic acids, those are ones that contain different numbers of chlorine atoms, different number of oxygen atoms bound to chlorine. This is our hypochlorous acid again, HClO is how it's usually written. But the bond that is breaking when it acts as an acid is this one right here, okay? The OH bond is breaking when hypochlorous acid acts as an acid and donates a proton. Well, the chlorine, of course, is electronegative, not as strongly electronegative as oxygen, but it's an electronegative atom, as opposed to hydrogen. If this were hydrogen, you just have water. Water, of course, is very, very weak acid. So suppose that we put an oxygen on that chlorine. So going from here, this is chlorous acid, the one we just looked at before in that little table. Now, oxygen is quite electronegative. Because of it withdraws electron density toward itself and weakens this bond. So as a result, chlorous acid is a stronger acid than hypochlorous by several orders of magnitude, in fact. If there were two oxygens here, this is chloric acid. Now there are two oxygens withdrawing electron density and making this OH bond still weaker. Chloric acid is almost, it's a borderline strong acid. The Ka is about 10 to the minus 1 or 2, or something like that. And finally, if there are three oxygens on the chlorine, this is perchloric acid. Perchloric acid is a very strong acid. Its Ka is on the order of 10 to the 10th or something like that. And you can see what effect there is of what are called electron withdrawing groups, the oxygens in this case, because of the high electronegativity of oxygen, it withdraws electron density from the OH bond and makes the bond weaker and weaker and very weak down here. So a way of looking at that, go down like this. This is, again, is taken from another book. I'm going to blow this up a bit, like that, so we can see these numbers better. So if we start over here on the left side, the very weak, this is hypochlorous acid. It's the HClO that we just talked about. So there's no oxygen on the chlorine. There's just this OH group here. Ka is about 10 to the minus 8th. Very weak acid. Chlorous acid has, excuse me, down here, chlorous acid has another oxygen attached to the chlorine, which weakens the OH bond. And so now the Ka is about 10 to the minus 2. Chloric acid is this one shown right here. And there are now 2 oxygens attached to the chlorine, weakens the OH bond even further. Now it's a strong acid. I think a minute ago I misspoke. I said that it's a borderline strong acid. It is a strong acid. The Ka is about 500. And so it definitely qualifies as a strong acid, stronger than nitric acid, in fact. And so finally, if there are 3 oxygens on the chlorine, this is perchloric acid, HClO4. And it's a very strong acid. The Ka is on the order of 10 to the 7th, sufficiently large that it's difficult to measure accurately. Now, one of the things that we can see in the same vein is something like this. This shows the Kas, here they call it the acidity constants. This is from an organic chemistry book. It shows the acidity constants, the pKas, of a series of organic acid, of organic phenols and alcohols. All right, we're going to focus just on the phenol one. Phenol is this stuff right here. Phenol is essentially hydroxybenzene. And you know that the benzene ring essentially has the 6 carbons, all of which are sp2. And so there are these 6 sp2 electrons drifting around on the benzene ring. They're called the aromatic sextet for that reason. Anyway, the Ka, the pKa of phenol is almost 10, which means that the Ka is about 10 to the minus 10. That means it's not a very strong acid. It's like 10 to the 4th weaker than acetic acid even. And what happens when phenol acts as an acid is it breaks this OH bond right here and leaves behind the benzene ring and an O minus. That's called a phenoxide ion. The phenoxide ion, because of how weak phenol itself is a very strong base, stronger than hydroxide, in fact. And so the point here is that this OH bond is apparently strengthened because of all of these electrons that are in the benzene ring. Now, if I add a chlorine on this molecule and put it at this opposite the hydroxide over here, that's called parachlorophenol. As you can see, it's not a whole lot different than phenol itself, just that one chlorine. But suppose I put 3 of them on in the 2, 4, and 6 positions. That's here, here, and here, all right? In that case, those 3 chlorines make this a much stronger acid. In fact, the pKa now is about 0.6. It increased the acid strength by 9 orders of magnitude by having those chlorines there, all of which are electronegative. They withdraw electron density from the OH bond and make the bond weaker and weaker so that it more easily forms the phenoxide ion. Again, this is an example of the kinds of factors that can affect acid strength by strengthening or weakening a bond between oxygen and hydrogen. Oh,